So electromagnetic waves, huge conglomerate of different types of waves. Visible light is just a teeny tiny portion of the whole electromagnetic spectrum. You've got radio waves and microwaves and ultraviolet and infrared and X-rays and gamma rays, all sorts of things. Like we did before, back when we talked about waves, we're going to talk about the intensity of our waves. Now, intensity is kind of a measure of how much energy our wave carries. Intensity, if you remember, is power over area. So power is in watts, which is joules per second. Area is the area that your electromagnetic wave spreads over. So for example, if you had a light bulb, if I had a lamp here with a light bulb in it, light from the light bulb would emanate in all directions except for a little bit from the base. So that area would be pretty much the area of a sphere, because the electromagnetic wave would be traveling out over the area of a sphere. A laser is a little bit different, because the light is concentrated into a small beam. So to find the intensity of your laser, you would need the power, and the area would just be the little circular area that the beam covers. Now, just to get a little confusing, the intensity in this section comes from what we call the Poynting vector. And yes, I did spell it correctly. The Poynting vector, our book uses a capital S to represent it. It is a vector, hence the term Poynting vector. S, excuse me, is equal to 1 over mu naught being our constant that we saw a lot with magnetism, and then E cross B, the electric field crossed with the magnetic field. Now, we already know that E and B are perpendicular to each other. They're always perpendicular to each other. So we can easily just call this 1 over mu naught E times B. I like to remember the Poynting vector in that it points in the direction the wave's traveling, because we know the direction of E cross B is the direction the wave is traveling in. So the direction of our S vector is the direction the wave's traveling in. This S value is the intensity. It is power over area. Okay. Now, the electric field and the magnetic field are both sinusoidal functions. They're both changing with time, which means the intensity of our wave is also oscillating with time as well. Generally, when we talk about light, what we want is the average intensity. So on average, what is happening? The average value of our intensity will equal 1 over mu naught times the RMS values of the magnetic field. That will give us the average value of the intensity. You can write this in terms of just the electric field by using the relationship that C, the speed of light, is equal to E over B. You could write it in terms of just the magnetic field. You can write it in terms of the maximum electric field and maximum magnetic field, because we know how to convert between RMS and max values. So for example, What is the maximum value of the magnetic field 1 meter away from a 100 watt light bulb? Now we can easily find the intensity. The average intensity, using our top equation, intensity is power over area. We know the power of our light bulb is 100 watts. The area in that equation is the area the light spreads over. Well, the light bulb emits light in all directions, minus the little tiny bit from the base where it screws in. So the area it spreads over is a spherical area. So we need the surface area of a sphere. The average intensity of our light bulb will be 7.96 watts per meter squared at that distance. If we get further away, the intensity will decrease. If we were closer, the intensity would be bigger. And that's because of this radius, the distance away we are from the light bulb. Are we okay finding the intensity? You good with that? Let's manipulate our equation. We want the maximum value of the magnetic field. Well, we know C is equal to ERMS over BRMS. So in place of E, let's put C times B. So C times BRMS. But we have another BRMS, so that's BRMS squared. But that's not what we want. We don't want the RMS value, we want the max value. We know that BRMS is equal to B max over the square root of 2. So if we put that in here, basically we find that S average is equal to C times B max squared. When we square the square root of 2, we're going to get 2, and we still have our mu naught. So that's our average intensity written in terms of the maximum magnetic field. So solving for B max, mu naught is 4 pi times 10 to the negative 7. Did that correctly, you get 2.6 times 10 to the negative 7 Teslas. Now, unit-wise, it's kind of hard to, takes a bit of processing to figure out the units. If you keep your intensity in watts per meter squared, you will come out with Teslas for the magnetic field. So if you're in the basic SI units, the regular units will work out perfectly. Questions? could easily find the maximum electric field at this point too. Using the same relationship, we know this is true for max values. So Emax would be the speed of light times Bmax. So if we multiply our answer times the speed of light, we would have our maximum electric field as well. Questions? The sun, the intensity of the sun approximately at our Earth location is approximately 1,350 watts per meter squared. So we could easily find the RMS value or the max values of the electric field and magnetic field emitted by the sun out here at our Earth's location in the solar system. Be the same process, only difference is we already have S average. So same equation would allow us to solve for Bmax, we just have a different S average value.